Welcome back to G Fun Facts Online. Today, we are dissecting a technological revolution that is currently invisible to the naked eye, but is violently reshaping the physics of the internet. It is the story of how we broke the speed of light, or rather, how we finally stopped slowing it down. For nearly 50 years, the global economy, the internet, and every piece of digital communication have relied on a single material, silica glass. We have pulled fiber optic cables across ocean floors and under city streets, building an empire on the assumption that glass is the best possible medium for moving information. But it turns out, we were wrong. Or at least, we hit a wall. We reached a point in physics known as the nonlinear Shannon limit, where the glass itself started fighting back against our data. The solution to this problem is not better glass. It is no glass. It is a technology called Hollow-Core Photonics. Today we are going to walk through how scientists managed to guide light through a vacuum, how they smashed a 40-year-old transmission record, and why this matters for the future of artificial intelligence. To understand why this is such a massive deal, we have to look at the flaw in the foundation of the modern world. Since the 1960s, fiber optics has worked on a principle called total internal reflection. Imagine a pipe. You have a core of ultra-pure glass in the middle, and you wrap it in a cladding of slightly different glass. When you shoot a laser down the middle, the light hits the boundary between the core and the cladding and bounces back in. It is trapped. It ricochets its way down the cable for kilometers. This was brilliant. It won Charles Kao a Nobel Prize. Engineers spent decades perfecting this silica glass, removing impurities atom by atom, until they achieved a signal loss of just 0.14 decibels per kilometer. That is incredibly efficient. But solid glass has three fatal problems that no amount of engineering can fix. Problem 1 is the speed limit. You might remember from physics class that the speed of light, c, is constant. That is true in a vacuum. But glass is not a vacuum, it is dense. The refractive index of silica is about 1.45. That means when light enters a fiber optic cable, it slows down by roughly 31%. For the last 40 years, the entire internet has been operating at 2/3 the speed of light. In a world of high-frequency trading and real-time AI processing, that 31% delay is an eternity. Problem 2 is the nonlinear Shannon limit. This was the hard ceiling. To send more data, you naturally want to turn up the power of the laser. But glass is a physical material. If you pump too much energy into a tiny glass core, the glass reacts. This is called the Kerr effect. The intense light actually changes the refractive index of the glass as it passes through. The signal distorts, it scatters, and it interferes with itself. Effectively, the medium screams back at you. You cannot simply turn up the volume on the data anymore. Problem 3 is chromatic dispersion. Different colors of light travel at different speeds through glass. Over long distances, your sharp data pulses get blurry, because the red part of the pulse arrives at a different time than the blue part. This requires massive, power-hungry computers at the receiving end just to clean up the mess. So the industry was stuck. The solution was theoretically obvious. Throw the glass away. Send the light through air. In air, the refractive index is basically 1. Light travels at its maximum cosmic speed. Air does not distort the signal, even if you blast terawatts of power through it. The problem is, light hates staying inside a tube of air. If you shine a laser down a regular pipe, it just spreads out and gets absorbed by the walls. You cannot use total internal reflection, because that only works if the core is denser than the cladding. If your core is air, which is low density, the light naturally wants to escape into the glass walls. For 30 years, physicists tried to force this to work. They built fibers that looked like honeycombs, but they were too leaky. The light would fade away after a few hundred meters. But then came a radical new design called nested anti-resonant nodeless fiber, or NANF. This is where the physics gets beautiful. Instead of trying to reflect the light like a mirror, this new fiber uses interference. Imagine a soap bubble. You know how you see swirling rainbows on the surface of a bubble? That is not reflection. That is light waves bouncing off the inner and outer surfaces of the thin soap film and interfering with each other. The NANF fiber uses this exact principle. Inside the hollow cable, there are tiny, nested glass tubes attached to the walls. These tubes are designed with such mathematical precision that when light tries to pass through them to escape, the light waves interfere destructively and cancel each other out. The glass membrane effectively becomes a perfect barrier for that specific frequency, bouncing the light back into the hollow center. The light isn't guided by density, it is guided by geometry. In these new cables, 99.99% of the optical power travels through the air. It barely touches the glass at all. This brings us to the breakthrough. For a long time, hollow-core fibers were fast but lossy. The signal would die out quickly. The gold standard for solid glass was 0.14 decibels per kilometer. This was considered the fundamental flaw because of something called Rayleigh scattering, literally the light bouncing off the molecules of the glass itself. You cannot fix that. It is a property of matter. But recently, researchers from the University of Southampton and their spin-out company Luminicity, which was later bought by Microsoft, did the unthinkable. They achieved a signal loss of 0.091 decibels per kilometer using a double-nested design. That number is critical. It is lower than the fundamental limit of solid glass. By moving the light into the air, they bypassed the scattering of silica molecules entirely. They proved that a hollow tube can carry a signal clearer and further than a solid block of glass ever could. So what does this mean for us? The most immediate impact is speed. In hollow-core fiber, light travels at roughly 299,000 kilometers per second, compared to 200,000 in glass. That is a 47% increase in speed. In the financial sector, where algorithms trade stocks in nanoseconds, this is a winner-take-all advantage. A hedge fund connecting New York to London with this fiber could execute trades milliseconds before anyone else. But the bigger impact is on artificial intelligence. Modern supercomputers are not single machines, they are clusters of thousands of GPUs connected by cables. When you are training a massive model like GPT-4, the bottleneck is often not the chip's speed, but the time it takes for chip A to talk to chip B. Hollow-core fiber drastically reduces this interconnect latency. It allows a data center that spans miles to act like a single, cohesive brain. Furthermore, this is a green technology. Because air doesn't distort the signal, we can pump vastly more power through the cable. This means the signal can travel further without needing to be amplified. Fewer amplifiers means less electricity and fewer points of failure. And because there is no chromatic dispersion, the digital signal processors at the ends of the fiber can be much simpler and consume less energy. We are talking about a potential overhaul of the Internet's energy footprint. Now, it is not all smooth sailing. There are significant challenges. Manufacturing a solid glass rod is easy. Manufacturing a glass tube filled with microscopic nested glass capillaries that have to maintain their shape perfectly over hundreds of kilometers is an engineering nightmare. The draw towers that produce these fibers require atomic-level precision. Then, there's the issue of splicing. You cannot just glue a hollow tube to a solid glass cable. The light would reflect off the interface and you would lose the signal. Engineers have had to invent entirely new connectors and adapters to plug this new air internet into the existing glass internet. However, the trajectory is clear. We are moving from the glass age to the air age. The barrier that stood for 4 decades has been smashed. The theoretical constraints that defined the bandwidth of the early 21st century are gone. Microsoft's acquisition of Luminicity suggests that the big cloud providers are already betting their infrastructure on this. Eventually, as manufacturing scales up and costs come down, this technology will trickle down from undersea cables and supercomputers to the wider network. Someday, the fiber running to your home may contain nothing but air, delivering the sum of human knowledge at the absolute speed limit of the universe. The glass ceiling is broken. The sky is the limit. Thanks for listening to G Fun Facts Online.